This video explores the 60-year-old dream of solar farms in space. The promise is infinite, uninterrupted, and pollution-free energy. The shift is moving from the if of the 1970s to the how of the modern SpaceX era. Terrestrial solar is limited by the atmospheric filter, which severely reduces the solar intensity reaching the ground. The orbital advantage is that a solar panel in geostationary orbit can be 5 to 12 times more productive than one on Earth, offering a total value multiplier of 10 to 24 times. The 1970s reference design, SPS 1979, was massive, a 50,000-ton structure, 10 kilometers by 5 kilometers, generating 8.5 gigawatts. It required hundreds of astronauts and would transmit power via a microwave beam to a 10 kilometers rectenna on Earth. The dream died due to the launch cost barrier. The space shuttle cost $54,500 per kilogram. The total launch cost for one 1970 station was estimated at over $5 trillion, which was deemed unfeasible, especially after the 1980 oil glut reduced political will. Reusable rockets were the catalyst for resurrection. Launch costs plummeted from about $54,500 per kilogram with the space shuttle to less than $3,000 per kilogram with Falcon 9, targeting less than $200 per kilogram with Starship. Technology advances in solar efficiency also contribute to this shift. Path 1, the modern microwave, exemplified by Project Cassiopeia, uses concentrated optics and modular assembly by robots. It dramatically reduces mass to 1,348 tons, with an estimated launch cost of $4 minus $5 billion. It is technically feasible, but has high capital expenditure. Path 2, the infrared laser swarm, uses a distributed architecture where satellites convert electricity to infrared lasers. It offers incremental return on investment and dual use for other applications. However, it is blocked by heavy clouds, and public perception of space lasers is a challenge. Path 3, selling sunlight, or the mirror strategy, involves orbital mirrors reflecting sunlight to terrestrial solar farms. The philosophy is simple. Don't convert energy twice, just move the light. This extends generating hours and provides on-demand light to reduce grid battery needs. The economics of the Terminator focus on the peaker strategy. Power is most valuable when the sun is fading and demand is spiking, typically from 5 p.m. to 8 p.m. Reflect Orbital targets this window, utilizing 7 to 30% of the time for service and the rest for recharging. The engineering challenge is the saturation problem, how to steer without fuel. The solution involves using reaction wheels to absorb momentum and magnetorquers combined with aerodynamic tacking to quote, 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 wheezing Earth's magnetic field and atmospheric drag, resetting the wheels without propellant. In material science, a weaker, stretchier plastic makes better mirrors. This proprietary polymer, coated in 2.5 micron aluminum, requires less force to flatten out wrinkles. Lower tension means a lighter structure and a cheaper launch. Light pollution is the elephant in the room. Unlike diffuse reflection, the Reflect Orbital design uses specular mirrors to keep the beam tight, minimizing spillover. The brightness is equivalent to a full moon, but focused. Orbits can be adjusted to avoid observatories. The trade-off is 12,500 satellites, providing an extra hour of global solar energy. Comparing the three paths, microwave is all-weather, but requires massive capital expenditure. The laser swarm scales incrementally, but is blocked by clouds and safety perception is a concern. The orbital mirror is the simplest tech, using existing solar farms, but causes light pollution and only services dawn/dusk. The physics of space-based solar have always worked. Economics were the only failure point. With launch costs targeting below $200 per kilogram, the Starship moment makes space solar competitive with natural gas. Energy is a tool of abundance, and the sun never sets in orbit.